All right. So thank you everyone for joining, and thank you to those as well who will be seeing the recording. And most of all, thank you, Lewis, for taking out time to do this for us. Super excited to hear what you have to say. And yeah, over to you.
Okie doke. Guess I'll just quickly. Can everyone see the slideshow and hear me well?
Yeah.
Okay. Right. So today I want to talk about a concept I've kind of had for a while. It's come from a lot of sources. I call it the Internet of Logs, and it's a response to a few different demands, and it's a good idea I've seen in a few different places. And I want to kind of sketch out how an Internet of Logs might look and why it might be desirable and why I think it will work. So let's have a look. So talk is divided into a few parts. I'll start with a brief introduction. I want to talk a bit about some of the things I've experienced in work and also things I've seen in the real life that kind of led me to this kind of strange idea. Things in industry that I've seen that seem to cry out for something like an Internet of Logs, mainly in supply chain. I'm very supply chain biased, but that's where I've been working. Um, I want to do a quick sketch of what an implementation might look like of this thing that I'm describing. Go over the theoretical basis, look at a few papers, and at the end will be my confession about this whole thing. So let's get stuck into it. So the basic premise of what I think is that we should be writing data to logs and we should be communicating with them, and that is the best way to do most distributed systems. And I would strongly say all distributed systems that have to operate in the real world, collecting physical data or data from devices. So we'll start with some definitions because this can get, a little bit in the air if we don't do that. So a log, when I say log, I simply mean an append only linear data structure where a thing happens, an event, you append it to the event, and another event happens, you append it, so on and so forth. So this is an immutable data structure, or more accurately, an append-only data structure, meaning you can't go back and remove an event. You can have like an event that cancels another event and so on. But essentially, it's like a list a list of information that grows. And when I say Internet of Logs, I want these logs to be decentralized. So what does decentralized mean? Decentralized means you can write to it. I call it unilaterally writing. You can write to it without coordination, without having a quorum, without checking with your neighbors, none of that nonsense. It's what was that movie with that guy? He said like always be selling. I say always be writing. You're just writing all the time. Don't worry about anyone else. Which uh, I think is also the idea behind local first. You write to your local machine first before checking with anyone else, before anything like that. The other part of it is multi-master. To expand upon multi-master, I mean that every log is its own source of truth. So it's a polycentric world in that sense. There's no nodes you can only write to, nodes you can only read from. You can read and write from every node. So it's quite that implies eventual consistency, which we'll get into a bit later. But it implies you can have a big number of topologies with that kind of flexibility. So yeah, those are the two basic definitions of what I mean by an Internet of Logs, and we're going to go into these in a lot more detail. So I think the Internet of Logs and its consequences will be like great for the human race. You'll be able to write data wherever you want, whenever you want, without coordinating. And because I think logs are the lingua franca of data, which again I'll go into soon, everyone has the ability to transform their data to whatever they need without being tied to a particular paradigm of database, be that SQL, be that relational, I should say, be that document, whatever. So it's about communicating what I think is the base data structure of data stores, and it's very much based around doing that first and foremost, recording and syncing. That's really what it's designed for. Everything else is kind of secondary. So seriously, this is what I think we should be doing for a lot of our databases, or at least a lot of the databases in the industries I've seen. I don't know if any of you have seen the late great Joe Armstrong, but he would often say that the world, the physical world, is eventually consistent because, you know, relativity. Each thing has its own clock. There's no universal time, and we sort of, to get from an eventually consistent world to a stronger model of consistency, we put an artifice in front of it. We put an artificial constraint in front of it. I say we embrace the world's eventual consistency. We all communicate by asynchronously sending messages. I'm asynchronously talking to you, and you're asynchronously hopefully receiving it, and maybe some state changes in your mind, and as a result of the message I've sent, and maybe state will change in my mind at the end when you ask some questions or come up with a point. I think that's how the world works. The world doesn't work with distributed transactions. That's not how the physical world works. You can add them on top, but there's limitations for that. Second thing, I think logs are ubiquitous. We're going to go into that in a bit more detail, but I see this same pattern everywhere. I would almost say it's the foundational data structure of all databases is the log. And I'm purely focusing on writes and sync. When we get into the industrial motivation for this, I'll explain a bit more, but a lot of the problems I've seen are not data query problems, are not even schema problems. They are, we can't record data here, and we can't sync it. So this is like entirely what my tunnel vision is focused on when I talk about the Internet of Logs. So I'll briefly about the experiences that led me here. So here's a picture of me. I'm on a farm. At the time, I was working a lot of agritech jobs or agtech jobs, which is, as you might guess, technology deployed in the agricultural field. And here I am walking down this, and I'm either about to or I've just started. We call it drenching, which is you have like this thing which sprays a chemical on their backs. It's a deworming chemical, and this deworming chemical actually smells really, really bad. It's not a nice smelling thing. But I had to go at that. We called it full ag tech immersion. I wasn't paid to do this. I just sort of asked if I could have a go because I was writing software for agriculture. And the ag tech world, at least the ag tech world that I was in, which is mainly the Australian scene, they had a lot of issues with connectivity. As you can kind of imagine, Australia has densely populated areas, but the interior of it and the agricultural parts of it are not densely populated, and they had connectivity issues. Slowly improving, but they still have them. And these Australian companies often struggled to deal with the fact that their customers, would not always have a persistent internet connection because most software, is written by people in air-conditioned offices for people in other air-conditioned offices. We kind of think of the internet as like a thing that's always there, or connectivity as a thing that's always there. And if it's not there, it's an error. We think of it as sunlight or, a natural resource like an ocean. It's just ever present. In this industry, that was not the case. And I thought this industry struggled, and I saw the struggles of this industry, and it kind of got my brain thinking. But we'll go on and see what else I've seen that sort of got my brain thinking. Oops, I have gone backwards. Here we go. Here's the picture. This is how I got red-pilled on partition tolerance. So I was working remotely. I was staying at the Airbnb farm, which was in the middle of nowhere. It was about a 30-minute, 45-minute. I think it was like a 45-minute drive for me just to get like a 3G signal. It was 3G, so it was like fairly remote. I had satellite internet at the house, but the sheep red-pilled me on partition tolerance because he actually chewed through the cable that was connecting the satellite to the house I was staying at. So for a couple of weeks while we got the local ISP to repair that, I had no internet. And a sheep chewing through a cable isn't often discussed in the literature of, consensus protocols. Use-stand replication doesn't really mention it. I don't think Raft mentions it. But these kinds of things happen in the real world, not always sheep. It could be a lot of times people dig underground, they'll cut a cable. It could be a weather thing if you're dealing with satellite internet, severe weather conditions. Even inside a large metropolis, with sophisticated high-speed internet everywhere, a lot of the time will still encounter this. Excuse me. A lot of the time you'll still encounter this with suburban trains going under tunnels. You get cut off. This kind of thing is everywhere. But this happening drew it into sharp contrast with what I'd experienced before. So it does happen, and it is a big deal. Around this time, there was another ag tech company in Australia. I didn't work for them, but I was kind of in that scene, and I talked to the guy a little bit, and he wrote this fantastic article. I don't know if you guys will believe this, but it was on LinkedIn, and it was worth reading. I don't know if you guys have ever heard those two things together, but this is one of those scenarios where that happened. A guy called Kenny Sabir, and very inspired by event sourcing and Greg Young, which we'll get into later. But he wrote this bit, and that struck a bell with me because I'd kind of known about event sourcing, but I'd never considered it a solution to the problems I was seeing with disconnected apps. And he said all the business logic and data available to help with decision making needs to be able to run on the mobile offline as well as on the servers. And we have remote customers with no internet connection at all, where they're only synced to the cloud as their fortnightly trip into town for groceries, which is the reality of how isolated some of these people in Australia are that are in agritech. So it was a real life example in the industry I was in, but he described how he had actually handled it in a principled way using event sourcing. So that was one of the first things that kind of got me onto this. The sheet cut me off from the internet, and then soon after that, I read this, and my brain started ticking over. But that wasn't the first time I saw things like this. I don't know if you guys know Alan Kay. Coined the term object-oriented programming. He was a computing pioneer at Xerox PARC. I won't get into the definitions, the conflicted definitions of what object orientation exactly is, but he said this. He saw the idea many different times. He would talk about how he was in the Air Force in like the 50s or 60s, and he saw like they'd kind of done pseudo object orientation by having all the procedures at the front of like a tape of a program, and the data structures afterwards, and the procedures kind of pointed into the data structures, which he found interesting. He was also studying molecular biology, and he would talk about how the different cells would communicate with each other with electrical signals without knowing their internal things. He had all these like things that he'd seen, and he came up with you see a good idea that's odd 4 times in 4 different costumes, it finally starts to make an impression. And here's the choice you have to make when you're faced with something new. And I think this is the choice I'm making, or I'm trying to make. He says you can take this technological advance and you could decide that it's a better way of doing the stuff I'm doing now. Or I can use this to continue on the path and I can use this to continue what I'm doing. Or you can say this is not a better old thing. This is almost a new thing. And I wonder what that new thing is trying to be. So as I talk about all these new things I discover that have kind of been used as what he says as a better way of doing an old thing, after a while I came to see them as a new thing in their own right. So this quote really resonates with me. So another area which was mentioned in that article by Kenny Sabir was event sourcing. His whole thing was based by event sourcing. So what is event sourcing? I don't know how many of you are familiar with it, but I'll briefly go over it. It's the idea that the source of truth of a database are in these self-contained things called events. So as opposed to create, read, update, the CRUD formulation, where your source of truth is the current state. And this way, the source of truth is the history of everything that's happened to your data store. It's a sequence of events. That's the source of truth. We'll go into that. We'll have a look at it in another light in a minute. But it was pioneered by Greg Young, I think, 15, 20 years ago. If you're into this kind of thing, definitely watch his talks. Popularized by Martin Fowler. I don't think I need to introduce who Martin Fowler is. He's a pretty famous guy. But he wrote an article that kind of got it on people's radar. And it came out of it didn't come out of the database community or anything like that. It came out of the software engineering community with the people doing domain-driven design. So that goes back to what I talked about before about ideas coming from different. Because as we'll see, this software conception, or this very software engineering focused conception of event sourcing actually has a lot to do with what we see internally in a lot of interesting systems. So I was listening to one of Greg Young's talks, and again, this I hate to use the word because it's overused now, but the synergy between event sourcing and systems that work offline was once again discussed. And his argument was that event sourcing was uniquely suited to handle these partially connected. So what did he call them? He called them occasionally connected, which is a way, I suppose, his way of saying systems that have a lot of network partitions. And he came up with 3 reasons why you might want that. One of them is that your clients can lose connections and they still want to do useful work, which goes back to what I said before about not wanting to wait around for consensus. Unilateral writes, always be writing. Don't worry about the internet. You just write. Sync later. Worry about it later. The second one is he talks about availability and how for a lot of scenarios, availability is preferred over consistency. I think the scenarios where availability is preferred over consistency are a lot bigger than we think they are. And I think part of the reason we often go for this distributed consistency, or I should say these stronger levels of distributed consistency that sacrifice availability to an extent, is because we don't really have the theories or tools to deal with them. I go over some of these later on. He talks about a bit about the availability consistency trade-off. I won't talk about the CAP theorem because I think there's an availability consistency one, but partition tolerance happens either way, right? You can't control that, which is an argument I stole from Martin Kleppmann. But anyway, you're favoring availability over a higher level of consistency, we can say. And the third reason is he's talking about throughput. Obviously, if you can write straight away when you receive something, if you can write to a data store straight away when you receive something, it's a lot faster than having to get a quorum or having to do a consensus. And which, if you think about it, is almost the same thing as partition tolerance. Because if you think about it, if you don't have partition tolerance, that's just waiting a very long time to do a write. So if you think about it that way, people have made this point before. So if you want to do a write really quickly, that also handles the case where you can't communicate with the outside world, because to do a write quickly, you can't do a network request. So these are two sides of the same coin. I've heard people say that the edge, which I think means putting servers closer to a user, right? I've heard people say that the edge or rather that local first is just the edge taken to its logical conclusion. And I think low latency writes and availability, I think low latency writes is just network partition tolerance taken to its logical conclusion, if we look at it that way. But he says this is a way to do high throughput. And I think he thinks he's going to see more and more people dealing with these kinds of models. And I agree. And this is what I've seen not only in AgTech, but also supply chain in general, which we'll cover in a bit. Oops. Where am I? I'm sorry. Give me 1 second. What have I done? Oh, there we go. Why? Sorry, we're good. Found it. Okay. I briefly mentioned Martin Kleppmann, and apologize for the rather poor photograph of this. But I thought this was a fantastic mathematical conception of what the event sourcing people were talking about. He kind of discovered it by himself, or I should say rediscovered it. I think it's like a universal idea. I think it's more like a something that it's not really invented by people. It's sort of something you uncover and you give a name to, in my opinion. But he came up. I love these equations, right? He uses like an analogy from calculus, and he says that the state of something is the integral, from the start of time to the current time of all the things of all the events you've recorded, and the opposite of that is all the events you recorded are a function of the state over time. And I thought that was a beautiful way to do it. I really like small equations because they make me feel rigorous, but that's also realistically all I can deal with. So yeah, I thought this was a fantastic little picture. if you read the very end of this, he goes on to quote Pat Helland, which we're going to get to. But yeah, the last bit is worth reading. If you store the change log durably, aka what I'm talking about with the log, aka what event sourcing people call events or the stream of events, says that it simply has the effect of making the state reproducible because you can always, of course, integrate over the state, right? If you consider the log of events to be your system of record or source of truth, any mutable state is being derived from it. It becomes easy to reason about the flow of data through a system. So the other thing he did is a talk called "Turning the Database Inside Out," where he talked about using Apache Kafka to do similar things. Oh, sorry, did someone have a question? What was that?
Yeah, sorry about that.
Okay, are we fine, or was there a question?
No, I think someone mistake by mistake left their mic.
Oh, no problem. Okay. Yeah, yeah, so Martin Klitman, again, I'm seeing the same idea in multiple different places. Martin Klitman also came to this conclusion. He was not involved in the DDD in the event sourcing world. So I thought that was interesting. He goes on to quote Pat Helland, and I want to quote him directly because I think Pat Helland represents almost like a third thing. I don't think he hit any hint from Martin Klitman. I don't think he knew about event sourcing or came out of the domain-driven design world. But he also came up with like the same idea. The old adage, accountants don't use erasers. It's an append-only data structure. You can't go back and remove it. But here we draw a link to not only sort of conceptual software engineering notions of events, but he also points out that this is how a lot of databases work. He says it's similar to database management systems in which transaction logs record all the changes made to the database. High-speed appends are the only way to change a log. From this perspective, the contents of the database hold a caching of the latest record values in the logs. The truth is the log. The database is a cache of a subset of the log. That cache subset happens to be the latest value of each record index from the log. So this, I almost don't want to say it because it's become a bit of a meme, but he's basically saying the database is the log, which apparently was controversial. I didn't think it was controversial. I thought that was self-evident, but apparently it is controversial. But let's explore that idea. Let's agree with that idea. He also goes on to talk about observed and derived facts, which ties in very neatly. Just briefly go back to what Clinton was doing here, right? The stream are the observed facts, and the state is the derived facts. Literally, he wrote like a derivative. So I thought that was neat. Accountants don't use erasers, otherwise they go to jail. So you can't, manipulate the log like that. They remain in the ledger. You can put corrections by making a new thing on the ledger, so it stays append only. A correction is just an event appended to the ledger. It includes things. But he says some entries describe observed facts, which is very similar to what the event sourcing people are talking about when they talk about events or domain events. So he gives the example, receiving a debit or credit, and then he talks about derived facts based on the observations, which is literally deriving the current state from the log, or rather, that's how I read it. So again, I'm seeing these kinds of ideas in multiple places using slightly different languages and slightly different metaphors, but they all seem to be saying a very similar thing. So as Ellen Kay says, when you see the idea in a few different costumes and it's new, maybe it's trying to tell you something, but there's even more. So strangely enough, completely the opposite kind of end of the software engineering spectrum, almost, is the 1997 paper. Why don't I have the name of the paper? It's called, I think it's just called the Log Structured Merge Tree. A lot of you are into databases, I think. A brief introduction, if you're not, a log structured merge tree is like a fundamental data structure to do CRUD operations. It's used in RocksDB and by extension, MyRocks and all the rest. Most key value stores seem to do it this way now rather than B-tree. But the interesting thing I saw, this paper goes into a lot of detail discussing the costs of like paging and moving things from one section of the disk to the other and moving things in and out of memory. But he talks about, or they talk about, multiple authors, they talk about appending to a log as if it's like basically free. He says, as each new history row is generated, a log record to recover this insert is first written to the sequential log file in the usual way. And he doesn't go on to talk about the performance properties of this or how this might be slow. It's basically like a no-brainer. He almost treats it as a no-op, as opposed to all the other things an LSM tree has to do. So again, the same idea. Even in foundational database structures, we see this idea that this sequential history, this log of events, this stream of events, this stream of observed facts. If you think about a write as an observed fact, whatever you want to call it, we see this thing where it's treated as the source of truth. You commit to it first, and that makes a commit, and things are derived from it and cached from it. It's the exact same idea. So, you're seeing the idea in multiple different places. And of course, RocksDB is probably the most, I feel like it's the most famous database that uses LSM trees. But, they talk about briefly their practical reasons for using an LSM tree. If you go to their wiki, every update to RocksDB is written in two places: the in-memory data structure called the mem table, the write-ahead log, the WAL on disk. And I thought this was interesting. In the event of a failure, write-ahead logs can be used to completely recover the data in the mem table, which is necessary to store the database to the original state. So again, I think the log is the database, because they're literally talking about how you can reconstruct the mem table, which is their in-memory key values representation of the current state, from the log. So they're saying they're restoring the database, but if I'm going to be a bit spicy, I say they're restoring the cache. This same engineering principle even applies to the internals of like a super fast key value store. And yeah, following on from that, it guarantees process consistency by flushing the WAL. So the consistency, the WAL being the write-ahead log, the consistency is a function of the log. Actually writing it to the bit where the user can query in a key value fashion is almost like a side effect of what's been written to the log. Again, observed facts, derived facts. SQLite, another famous example. They define a transaction by you having committed something to the write-ahead log. Commit occurs when a special record indicating a commit is appended to the WAL. Thus, a commit can only happen without ever writing to the original database, which allows readers to continue operating from the original unaltered database while changes are simultaneously being committed to the WAL. So same idea. I'm seeing the same idea over and over again in all these incredibly popular databases. But the thing that all these popular databases do is that they make the log an internal detail. And again, this is my last example, I promise. Again, Postgres, they also love logs, and they talk about like a bunch of fantastic reasons why you want to do logs. Right? They talk about how if you follow the procedure, we do not need to flush data pages to disk on every transaction commit, because we know that in the event of a crash, we will be able to recover the database using the log. I think this means the database is the log, right? I'm just saying, any changes that have not been applied to the data pages can be redone from the WAL records. Again, observed facts, derived facts. Yeah, so I'm seeing this a lot. I'm seeing it in the world's most popular databases, even when obviously their read model and their write model look nothing like a log, but they're all using logs internally. Following what also the software engineering people have discovered, it's all kind of converging for me. So based on all this, I am forced to conclude this about logs. They're super efficient. Append-only data structures, whether that's a file, whether that's something in memory, is a very efficient thing to do. These papers treat it as a no-op. These discussions of writing to the WAL and relational databases before they do anything else, because of all the data they have to transfer everywhere when it's all over everywhere. They also treat it as basically a no-op. They write it to the log first because it's cheap and easy to do. It also seems to be, this is more controversial, but it seems to be the universal data structure. Now, there are, of course, databases that don't use the log. The most prominent example I can think of, and maybe this is my ignorance of database implementations, but it's Howard Jew's Lightning Level Map database, LLMDB, which does not use the log at all. But again, MongoDB also uses the log. I think SQL Server has a write-ahead log. They're all using the log. So it seems like a foundational data structure, and almost what I'm thinking about is turning this foundational universal data structure of a lot of prominent data stores into a lingua franca to communicate between them. But I'm getting ahead of myself. Any read scheme can be projected. You can create a key value store out of a log like RocksDB. You can create a relational database out of a log like you can with Postgres. So it seems to be eminently flexible with what you can derive from the information. And we'll get into this a bit more later, but it's very easy to reason about a log for syncing. That is the last conclusion I make. So that's a bit about my experience, what I've seen in a million different places about why this technical solution is a good solution. And I know this may not be a huge amount of interest to you guys. I won't spend too much time on this, but I spent most of my career programming in the supply chain. And I notice that supply chain people talk about different things. Supply chain is a really weird industry because it's a huge industry, but it's not really mature in terms of technology. Like they treat it as like this black box. Like, look at this picture. This is from Forbes, right? This if you search supply chain tech, you come up with so many of these funny pictures with like holograms and like ships that are also databases and stuff. I mean, they think supply chain technology is a dude with a phone in the warehouse. Like, I don't know what he's doing. The phone has like gears and a cloud and a plane and a shopping cart and a Wi-Fi symbol and an icon of another computer. This is what this one of the world's biggest industries thinks about technology. And I'm going to go if you read what they say, a lot of their problems are the inability to share data. But let's look into that a bit more. So the state of supply chain data. There are many business-driven initiatives in supply chain data around sharing data. They're obsessed with sharing. They're obsessed with collaboration. They recognize the problem that in that industry, and probably in a lot of other industries, right, that they have siloed data. That one company or even one department has all their data in one place and it's locked in there and it can't communicate. So they're very aware that this is a problem for them. Their solutions are kind of funny, but we'll get into that in a second. So yeah, they want to share data. Cool. Why do they want to share data though? Why the big drive to suddenly collaborate and share data, not only across different businesses, across different parts of the supply chain, but also within a supply chain, within a single organization? There's a few things. Post COVID-19, people have been very concerned about disruption to the supply chain, and they want supply chain resilience. And meaning the push behind JIT stuff has kind of gone away, and they're more worried about being able to handle disruptions and still serve their customers. Because obviously, the supply chains that could handle COVID did really well, right? The ones that couldn't, not so much. The other thing they really want to know about is real-time visibility. If they can communicate things with their partners, with their suppliers, with the people they send things to, and they have a lot more information about what's going to happen, and there's less invisibility, there's less speculation, this is somewhere in transit, but we don't know where, we don't know when. That is a huge competitive advantage. And, for real-time visibility, you need to share things between different parts of a supply chain, between a warehouse, between a distribution center, between a transport, whether that be a truck or a ship. That kind of thing is impossible. You need to be recording data at all of those places in order to get visibility, and you need to be sending that data. Another reason is this is mainly in the EU, but I see this in the US to an extent, and other Western countries to an extent, is there's ever increasing legislation. I don't know if you guys are aware of this, but like companies in Europe need to be able to say that this material was not produced in a foreign country by things like slave labor, or this battery, or this part for a machine didn't have the diamonds from a diamond conflict area, all sorts of things. Also about what do they call it, environmental practices. This I don't know, chair that's made of wood wasn't cut down in an endangered rainforest. All sorts of things. They've been increasingly forced to by very expensive fines, like percentages of global revenue, to be able to prove certain things are quote unquote ethically sourced. So there's a big pressure to comply with legislation, and these companies simply do not have the data because they simply don't record it, or if they do record it, they simply don't share it. So yeah, this is their hierarchy of needs, right? They need to be able to make better decisions and have more insight, and to do that, they need more information, and to do that, they need more data. And to get the data it needs to be, they need more flexible data sharing topology. But the big thing is, maybe this isn't the case for other industries where you can have a big centralized server, and it's kind of fine. This kind of isn't working for supply chain anymore. The data is inherently distributed. It could be between companies that data is distributed. Obviously, two competing companies or even two parts of a supply chain that cooperate, on the same entity, obviously have their own source of data. That's pretty normal. You're all used to that. Even different departments might have their own sources of data, their silos of data that they're hoarding. Maybe transport doesn't want to deal with warehousing, or rather maybe they both have their own data systems that don't communicate. Very, very common. And physically, the real world data that you can ingest as you move across the supply chain, including the transport phase, means that the data is distributed physically. There's companies now that have IoT devices inside of shipping containers that measure things like the humidity levels or the temperature levels to make sure there's no fluctuation, to make sure your refrigerated shipment of strawberries or mangoes or whatever isn't sitting on a dock in Hong Kong in the sun, festering away. so they have things now that can measure, and then they can say to their transporters, hey, this was sitting in the dock for 2 hours, it's ruined, we can't sell it. So they're trying to, there's also like physical data that they need to gather in order to form a bigger picture of what's happening in the supply chain, especially around the conditions of goods. Come across this great article by he's been doing supply chain tech consulting and data consulting for like 30 years. The name of his article is up there, but he said something very pertinent. Supply chain data is fragmented with no single source of truth. Most systems are challenged to leverage a vast amount of data within each of their business systems. This is because their data is fragmented, locked in individual software application silos. Thus, most supply chains only have rudimentary data interoperability between their systems and external systems. Right? You may notice this in other industries. I'd actually be really curious to see if you guys and other business verticals have seen these same problems. I'd love to hear from you after the talk. But in supply chain and logistics, definitely a huge deal. And this is one last thing. This is from Brookings. US supply chains are a collection of decentralized systems, each with their own objectives, decisions, rules, blah, blah, blah. Challenges regarding data quality, availability. I should have highlighted that. Availability. I'm big into high availability, which means partition tolerance, right? And immediately increase when attempting to coordinate and manage multiple supply chains and their multimodal logistics and infrastructure. Data is rarely shared across supply chains and only occasionally spread across firms in the supply chain and logistics industry. It's a hurdle for shippers, carriers, customers, employing different technologies. And they give an example of two. I think these are the two largest ports in the United States, I'm guessing, or the largest in the West Coast and largest in the East Coast. Use completely different software platforms, cannot communicate with each other. Oh, one last thing. These people think blockchain will help them. I wrote a whole article on this. It's they have no idea. They have no idea what blockchain is. I think it's got chain in the name, and they're in supply chain, so they just think, look, it's got chain in it. We're in a chain, and also it isn't emailing spreadsheets, so it's new and novel. So this is probably what it works. But if you read anything, I kind of recommend reading my article if you're a little interested in this, because they basically think that blockchain is like a distributed database. That's all they view it as. They just view it as a place where multiple people can write to and share data, and somehow they think you need a blockchain for that. So again, this goes to illustrate the huge, as an industry as a whole, the huge technical gap that they have, despite being such a valuable industry. It's not fintech, folks. This is what I'm trying to say. It's better than ag tech, but it's not fintech. Yeah. So the implications for this, wrapping up the industrial part. Local first, that you need to always be writing. Whether it's in the shipping container, in the truck, whether it's in a part of the warehouse that can't communicate with the other warehouse, whatever. You can't be waiting around. Also, distribution centers get power cuts, which I've seen before, experienced before. Meaning everything comes to a halt because they can't write the data to the internet, right? It's a polycentric world, so you need a polycentric database. Machines are super powerful now. You can have a database in like a barcode reader. There's barcode readers, and the supply chain calls them handheld PCs, but they're basically like a little Android device. And how many bloody thousands of events a second can an Android device do? Even like a modest one doing SQLite, it's thousands a second. If you think about, you're not going to saturate it, as I guess what I'm trying to say. We can record data on handheld devices. We need to get away from this, big machine can only do it mindset. So it's polycentric. the data is collected in polycentric areas, and if you should write it where you record it. Is my basic thing. That's local first, writing local first. They're hyper-connected. Supply chains are literally a chain. Different companies, different firms, from here to there, from the transport people to the receivers to the dispatchers. It's a chain that needs to be connected for parties to have full visibility to tackle the challenges I mentioned before. And also, if you listen to these people, business people I'm talking about, these aren't technical people, talk about supply chain. They talk about events. They talk about things that have happened. They don't talk about the current state. They talk about this shipment hasn't arrived. This shipment was dispatched. This was checked for quality control. This was picked. This was packed. Those are events. They talk about events. So why not give them a log of events? Right. Now for the completely opposite, I want to talk about the theoretical basis of why I think this will work. I will admit this part of it is probably my weakest part. And in this part of it, if any of you guys, I know some of you, like Vipul, are real wizards at this kind of thing. If you've seen gaps in my reasoning, please let me know, because I want to know. I'm not going to be embarrassed at all. I would rather know and shore that up than operate under ignorance. But I think I have a fairly good theoretical basis. So we'll go through and have a look at that. So a bit of a spicy take. CRDT, the foremost misunderstood letters in distributed systems. When people hear CRDT, I think they imagine, I don't know, like a collaborative app for writing stories or editing cat pictures or something, which is all well and good. But I really don't think that's the core of what CRDTs are, and I really don't think that's the reason they're industrially interesting for me. The name is also not that good, because if you look at the literature and the theory behind it, they don't really describe anything that's conflict-free. It's just that they resolve the conflicts in a certain way. They're still complex. Also, they don't necessarily describe data types. These are more properties of systems, but we'll have a look at this. If anyone wants to get into CRDTs in a more principled way, just read this paper. I think this was the original paper, or it might have been like the second variation they did. It's from 2011. Two of the authors here, Nuno Preguiça and Carlos Pequero, are like distributed systems wizards. They've written like papers since like the late 90s. They know their stuff. They know about all sorts of logical clocks and all that kind of thing. So yeah, highly recommend this paper. We'll have a look at a bit of it actually right now. So a brief introduction to causal history. Causal history is limited to a single replica. Is basically the sequence of events in the Lamport sense that a replica has received. We can think about an event as an update, right? So if we look at this, it's a sequence of events. They talk about how it doesn't include queries being read-only. We don't worry about them. But it's the sequence of updates that a replica has received. It's its causal history. So this is a conceptual way to think about any replica that stores data. It has a causal history of updates that it has seen. Note at the very end. Sorry, this is a bit. If you haven't seen this paper, this is like a lot of stuff to read. But basically, think about it, as like a sequence of updates that a single replica has received. And at the end, they say, note that the causal history is a formal reasoning device, normally not needed in a concrete implementation. As you may have guessed, I have ignored that because I think that a log is a concrete implementation of a causal history. So I have ignored that part of it. And we'll go and see why. Again, they talk about deriving state from causal history. What does that remind us of? What does it remind us of? It reminds us of the event sourcing people deriving the current state of the application from the stream of events. It reminds us of Martin Kleppmann literally deriving the current state of the application from the stream of events. It reminds us of Pat Halland, his observed facts, his derived facts. It reminds us of the write-ahead log. The writes go there first, and the state of the database is derived therefrom. And now we tie this in to a concept called strong eventual consistency. I think strong eventual consistency is the whole point of CRDTs. They are just a tool to achieve this. And there's a small equation here, and it's just if the causal history, I and J represent, equation at the bottom, I and J represent replicas. All it's saying is if the causal history of two replicas are the same, it implies that their state are the same, or that their state is the same. Meaning if something, if we think about a web server, if something has received the same set of HTTP requests, if it's strongly eventually consistent, the state will be the same. So CRDTs are basically a tool to achieve the strong eventual consistency. And strong eventual consistency, in my opinion, just describes eventual consistency in a multi-master sync that actually works and is predictable. I think that's really the core of what a CRDT is. And I highly encourage you to read this paper, especially the first section, which I'm quoting from now, and really get what the big idea behind CRDT is. It's not YJS or the other libraries, not to take anything away from them, but the huge collection of data structures they come up with is not the point of what a CRDT is. It's a way for eventual consistencies to have predictable and behavior you can reason about.
Hello.
Sorry, go ahead.
Yeah, I'm sorry to stop you, but I think I have to ask it here. So, how would you compare the popular implementations of CRDT with your the strong eventual consistency idea of CRDT, which you just mentioned? For example, you talked about YJS, or what about auto merge, etc.
Okay, to clarify, they are CRDTs. I don't think okay. CRDTs, if you read the paper, all they are is a tool to achieve this equation. That's how the paper introduces it. They describe a series of data structures, or sort of not even data structures, sort of abstract data types that can achieve that. If you follow the rules of them, they can achieve this strong conversion. So auto merge and YJS are fantastic libraries, but as a second order thing, people read about these libraries and they think that CRDTs are like these JSON data structures that you can merge. And that's not the big picture at all. I don't know if I'm explaining this well.
No, I think it makes sense. It definitely makes sense. So I mean, it feels almost as if CRDTs are a abstraction on top of JSON data structure, if you don't truly understand this equation or the idea which you are mentioning here.
Yeah, pretty much. Like, this is the big idea. I quote this paper all the time, but there's like a paper from 1982. The name of it's Parker 1983. I can't remember what it's called, but it's basically about they come up with the proto CRDT. They come up with the CRDT before the term existed. We're talking about distributed file systems that can be edited without things. So it's like a thing basically you find almost in nature, and that they've formalized in 2011. I just think, I really want to stress to people that, like, this is the big idea behind them, not auto merge. Great library, but that's not the big idea. Yeah.
And just one last follow-up question. So when you use CRDTs in your project, what do you do? Like, do you have your own implementation, or do you think the standard ones are fine?
I'm interested in whether CRDT is a whole database, which I'm going to get into actually now.
Okay.
So hopefully I can explain this.
Thanks, Vaibhaw.
Yeah, no problem. Any one of you guys have questions that, like, I'm going to forget about, or you're going to forget about, feel free to interrupt. It's fine by me. So we've talked about we've talked about how we get from these events, these logs, these whatever, to the current state. And one way to think about this is a reducer. And I'm kind of regretting not writing what a reducer is. I hope you guys are all vaguely sorry about this. I hope you guys are all vaguely familiar with functional programming, and you're kind of like familiar with, like, folding over a list and you get something out, right? Or reducing over a list, or whatever it's called. Okay, good. Or aggregating, yeah. So I've called this thing that goes over the sequence of states or the sequence of events the reducer. And these are some good algebraic properties of a reducer that you can have, so that this makes sense. So that when you fold over CA or CJ, you get the state that matches, regardless of what they are. You're folding over a set in a sense, not a sequence. It has to be commutative. The order of operations doesn't matter. It has to be idempotent. You can repeat the operation, it will come out the same. It has to be associative. Again, this is an order thing. And we sometimes think of these as quite abstract, algebraic properties of something. But what are the real-world implications? What do these properties imply? These properties imply real-world things about distributed systems. Idempotent implies that you can resend it over and over again, because messages get dropped and you may not receive an acknowledgement. It's a property of a system being very resilient. Commutative and associative implies that messages across a network can be reordered. They may be dropped. One may get there faster. One may take a different route. It's basically these algebraic properties basically relate to real world resilience on real world network conditions. On farms, on trucks carrying goods that may not be connected. It's literally a real life application of these algebraic properties. So that's what that's what these properties imply. That's why they're there. They're there to handle network partitions, which you see all the time in the real world in the physical delivery of packets across a network. Right. I'm hoping my justification here makes. Oh, sorry. One I forgot. The reason why I bring up these three properties as well is because this, if you look at the CRDT paper, these are the properties that the CRDT merge operation has to have in order for it to be a CRDT. It's in all the papers. So everything on auto merge follows these properties. Everything in YJS follow these properties. So what I'm saying is logs are the base of a log, or the observed state is not only itself a CRDT, which I'll go into a bit more detail soon, but also the things you can derive from them. You can derive from them in a CRDT way, so that even if your set of observed facts on one replica is in a different order from your set of observed facts on a different replica, if the set of observed facts are the same, even though through syncing they might be in a different order, the current state can be the same if the way you derive the current state from them follows these three laws, which are the algebraic laws for a CRDT merge. It all comes in a full circle. So, part 4, implementation. This bit is how am I doing on time, by the way? Oh, geez, I've spent more time than I thought. I'll try and get through this quickly.
Yeah, no problem. I think we have time.
Okay, part 4, implementation. This is the basic architecture I have in mind. There's log A and a log B. You communicate by message passing. This is actor model stuff. So it's pure message passing, as in you don't rely on an acknowledgement from a request. You may get one, you may not, which ties back to idempotency, what I talked about before. Each log has a filter on the messages it receives and wants to actually append to itself. It can filter that. There's also an outgoing filter on the logs that it sends, or rather on the logs that it sends. Sorry. Or an outgoing filter on the events that it sends to other logs. So there's a two-way filter, so you have some degree of freedom that allows things like bidirectional replication or unidirectional replication if you want to do that. If you only want to have like a feeder system where a bunch of logs feed into a central one. It's basically for a network, the freedom of network topology, or allowing a large number of network topologies, you have to have filters. Basically, with bidirectional sync and filters, you get pub/sub for free out of a multi-master system. You can formulate pub/sub in terms of this. So it's very flexible. So the way I envision it working internally is as an append-only file, which is the source of truth. The event ID, because each event has to be uniquely identified across the network, is what I would call a composite ID. It's the replica ID plus the index and the log. Because it's an append-only log, because each replica has one log, the ID of the replica and its position in the log uniquely identifies something globally, provided the replica ID is globally unique, right? That is a unique identifier for that event. Each log should have a map of replica IDs to a vector of log positions. This lets you quickly look up something in the middle of a log. This idea I didn't actually steal from Bitcask. There's a paper about Bitcask, which I think was from REAC. But it's the same idea if you're familiar with that. Basically, you keep all of this in memory so you can quickly look it up, but it doesn't actually grow that big. And it's a map because this way it's actually a version vector in disguise, because the length of the vector becomes the update number. So this is actually a version vector in disguise, as well as being a lookup table. Two birds with one stone. And you sync by looking up this thing, by looking up in the map what events haven't they seen, by comparing the sequence numbers and saying, okay, they haven't seen these. We'll filter out the ones that are from their ID because they could have been sent from another node. And we can send across, not completely, we can't avoid sending redundant data because two nodes, node A and node B might have both received data from node C and they have no way of knowing, but you can reduce the amount of redundant data that you send. I have to test this a bit more in theory because it may be more redundant data than I think, but I think it's just the math seems to work out anyway. The implementation idea I have in mind is very LMAX inspired. LMAX again goes back to Martin Fowler. Martin Fowler, he had to talk about event sourcing, and he mentioned that LMAX kind of did event sourcing. Also, the inspiration for Tiger Beetle, or one of the inspirations for Tiger Beetle, is LMAX. So LMAX seems to be a very influential piece of software. Basically, it was a low latency financial trading platform. Their big idea was that data should uniquely be owned by a single CPU core. I'm not a CPU wizard, but apparently that means that you have less crossing cache lines and things can be a bit faster. So I think, great, I'm going to steal that idea, and I want a one-to-many relationship between logs and CPU cores, as in one log cannot be owned by any more than one CPU core. I think that would be still pretty bloody fast, because appending to a file and updating a table of memory is like a super fast thing to do. I think you'd be hard pressed to saturate that, but more testing required. And the other thing LMAX did is they had the projections entirely in memory. We talked about before about how the whale was how the write ahead log, the whale was was the source of truth, and the database was just a cache. Well, these people took it to the extreme, and they made quote unquote just the cache literally just be in memory, because if the machine went off, you could recreate it. I thought that was a super powerful idea. I also think that would use a lot of memory, so maybe that would only be viable in certain high performance scenarios. But yeah, I think that's worth mentioning. You have different options if you're deriving the state of the application from a log. You have a lot of different options you can go ahead for with different performance requirements, different hardware budgets. A brief example of what it would look like here. I was trying to represent like the variable topologies you could have. So if you imagine a local server here having many logs, and there's sort of being these sort of standalone logs and sort of small handheld devices, IoT devices, handheld computers in a warehouse, smartphones might have a couple because they're a bit beefier. And you can either sync bidirectionally with these storage, you can sync one way, that works well, and then you can sync from a local server to a cloud server, to literally have a backup and share data with other local servers. So the way I've envisioned it, the topology can be super, super flexible, right? Having a flexible topology and being resilient to network collision is like the whole idea for this. And I want to finish this up with my shameful confession, which is I've kind of been working on this for a while, but I've been a little bit stuck. And one of the reasons I made this talk is because I wanted to see if I'm just crazy or this resonates with anyone else, basically. So if I was just crazy and this resonates with no one, that's fantastic. I read a lot of papers. I learned a lot. If it resonates with some people, but only for certain things, I would love to know what those things are. Or if people think it's a great idea, that would also be fantastic to hear that they think it's a great idea, or they can or even see other applications for it. But honestly, I wanted to get this out into the world and see if it made any impression on people at all. And if it didn't, I will probably start a new side project. So yeah, that is my shameful confession. It was kind of this whole talk was kind of a thing to see whether I should continue. Even if it comes to nothing, I still learned a hell of a lot, to be honest. And yeah, that's me wrapping up. Do you like the pun of the guy rapping and he's pointing up? I thought it was good. Yeah, any questions, especially any pushbacks or any things I've missed or things I've gotten wrong with the theory? I'm really keen to hear. I encourage a robust discussion. So yeah, that's it for me.
Um, Thank you, Louis. I mean, this was a fantastic talk. I don't have anything to push back on. I have a lot of things to read on. Um, and but can you also share the interlog project's GitHub or your GitHub ID, because I'm not able to find it via
Yeah,
Google.
share that in the Zoom or the Discord. What's better?
Yeah, anywhere.
Okay.
Discord would be better, I guess.
Yeah,
I might as well just do both. I'll be redundant with my data, right? Self-replicate it. They can be there. And it can also be in the Discord.
I will share it on the Discord. I will share it on the Discord with the recording. Okay, that will just keep knowledge at the same place.
It's very
All
much
right.
work in progress. I don't have any. I've only got the local log working, and I think it may crash. But yeah.
Yeah, that's not a problem. I mean, but just want to say a few words before I turn off the recording, and then we can do question answers. So thank you, Louis. It was really great, very well crafted talk. It kept me engaged throughout. So thank you for taking your time. It was a brilliant talk indeed. That's what Shraddha is saying in the chat as well. Brilliant talk. Got got a lot of resources to read through. Thank you so much thank you so much, Louis, for taking time. And yeah, that's what. So thanks again. So with that, I will just stop the recording and we will do question answers.